Hey everybody, let's talk about aircraft control surfaces and their components. Aircraft can range from real simple home-built machines to complex fighter jets like the images below indicate. But all aircraft have common structural and control components that allow for controlled flight. And aircraft stability is the characteristic of that airplane while in flight that causes it to return to a condition of equilibrium or steady flight after it's been disturbed. Aircraft can be controlled by shifting the pilot or passenger weight like in an ultralight or hang glider, or you can have surfaces that you manually move or use an electronic system to move to redirect the orientation of that aircraft. The fuselage is the typically enclosed space that holds the cockpit and cabin. The cockpit is the term for the area where the pilots control the aircraft. The cabin is where the passengers sit or cargo is stored. The fuselage serves as the structure to which parts of the aircraft are attached. The wings provide lift when sufficient air is flowing over them. Wings are attached to the fuselage at the top, middle, or lower portion and are referred to as high wing, mid wing, or low wing, respectively. A single set of wings is called a monoplane, whereas two sets of wings are called biplanes. The wings have flaps and ailerons that are attached to the trailing edges. Flaps are closest to the fuselage and are deployed downward equally on the left and right wing to slow the aircraft while producing more lift. Ailerons are moved in opposite directions of each other and they change the direction of flight. The empennage, or tail, helps the aircraft point into the relative wind like feathers on an arrow. The empennage consists of four major components: vertical stabilizer, rudder, horizontal stabilizer, and elevator. These are used to maintain stability and change the aircraft attitude or direction relative to horizontal with wings that are level. The landing gear absorbs the energy of landing and supports the aircraft while on the ground. The strongest sets of wheels are in the center of the aircraft, closest to the center of gravity. The other wheels are either located toward the rear of the aircraft, a tail wheel configuration, or toward the nose of the aircraft, a nose wheel configuration. The nose wheel configuration is also known as tricycle gear. Landing gear can be fixed so that it remains locked in place during the entire flight, and landing gear can also be retractable, which is more expensive and complex, but much more fuel efficient. Power plants come in many forms. In the case of the small aircraft shown here, the power plant consists of an engine and propeller. Propulsion systems will be presented in greater detail later in this curriculum. You should pause the video and attempt to identify the parts that are labeled with the green arrows before I reveal the solution. Did you get them right? Notice, if you will, the horizontal stabilizer has an elevator. The elevator is very similar to an aileron. However, one side moves down while the other side also moves down. One side will move up while the other side will also move up. They both go up and down the same amount and they move in the same direction at the same time. Whereas with ailerons, to induce a roll, we have to tip one wing down and the other wing up. So we have to move the ailerons respective to that. The rudder, there's just one of them, is on the back of the vertical stabilizer, and it controls yaw. It acts very similar to how the elevator and ailerons act in that it moves, in this case, left and right. But the horizontal stabilizer, the vertical stabilizer, and the wings are pretty much the same, which means that they have some camber to them and they allow for a change in force, whether that be a lifting force or a force that allows you to have a lift in a horizontal direction that induces yaw like the vertical stabilizer does. Notice how the flaps on this airplane are very close to the root of the wing where it attaches to the top part of our fuselage. And notice how the ailerons, also on the trailing edge, are more towards the wing tip. And one last thing to point out, on this horizontal stabilizer, on the back or trailing edge of it, where the elevator is, on the right hand side, there is a small, thin tab. This is referred to as a trim tab. We're going to see this labeled in another example on the next slide. Here we see an older military aircraft. It has that rear wheel, that tail wheel configuration, also a lot of times referred to as a tail dragger. This one has a much larger rudder. Look at it compared to the size of the vertical stabilizer. Also, look at the elevator and the rudder. They both have that trim tab. This tab allows you to hold a position of your elevator, rudder, or even ailerons if you have a trim tab on them. Let's take a look at another example. Here we can see the U.S. Coast Guard airplane. Its cockpit has been labeled, and behind that is the fuselage. You even have wings that are attached, just like the general aviation one, in a high wing configuration. We also have power plants. In this case, there's 4 of them. They're located in an underwing mounted position. There's an empennage at the back that consists of that vertical stabilizer and rudder, and a horizontal stabilizer and its elevator. Notice that the flaps take up a large portion of the trailing edge of the wing, and the ailerons take up very little at the tip. The same can be said about a remote controlled airplane. You still have a cockpit, a fuselage, a power plant, wings, again in this case, attached to the top of the fuselage, so a high wing configuration. And you have an empennage with your rudder and vertical stabilizer, and your elevator and horizontal stabilizer as well. Flaps and ailerons taking up the trailing edge of the wing. In this case, it looks like it's roughly a 50% flaps and 50% aileron on that trailing edge. Inside this crate, we can see that even the fuselage itself is made up of very light components that are pretty much in a truss configuration. This is a fuselage frame, and aircraft components in the skin will be attached to this to build the rest of the airplane. In this image, we can see how some of those components start to come together. Not only can we see the fuselage frame toward the back end where that tail wheel is, and we can also see the frame of the rudder and some of the vertical stabilizer, but we can see inside the wing as well. This wing also has a truss design. The wing strut itself consists of 2 triangles, and then you have the ribs, which consists of very tiny triangles, one repeated after the other to make up the airfoil shape of this wing. There's a leading edge and a trailing edge, and in the trailing edge we can see how some of that frame continues as part of the structure for the either ailerons or flaps. And then we can see that running between the truss for the ribs and the part of the wing structure for the aileron and flap is a spar, a beam that gives strength to the wing. The strut holds the wing up when gravity is pulling it down. And notice the smaller of those 2 triangles for the wing strut. It helps keep the wing from ripping off the top of the airplane due to the load put on it when generating lift. Let's talk about wings a little more. Winglets are vertical extensions of a wingtip that are used to limit air from recirculating from the high pressure airflow below the wing to the low pressure above the wing. This recirculation induces wingtip vortices and increases drag. The winglets help smooth out that air, reduce the wingtip vortices, and therefore reducing the subsequent drag. You should be pretty familiar with center of gravity, also referred to as CG. This is the point where the weight of an object is balanced. You can find a centroid located on the line of symmetry, and if you have 2 lines of symmetry, then it's going to be located where those 2 lines of symmetry intersect. The center of gravity is important when it comes to talking about the balance of the airplane. And balance, stability, controllability, and maneuverability are all what help us determine the effectiveness and efficiency of an aircraft. So knowing where that CG is located and making sure that our components cause the aircraft to maneuver around that CG is what helps us determine if the aircraft's control surfaces are effective in their use. Aircraft design often requires a trade-off between stability and maneuverability. Training aircraft are typically more stable to compensate for students' developing skill level, whereas fighter jets are typically more maneuverable and less stable to maximize the aircraft's tactical value. As stated earlier, an aircraft's stability is the characteristic of an airplane in flight that causes it to return to a condition of equilibrium, or steady flight, after the aircraft has been disturbed. An aircraft with positive stability returns to steady flight after that disturbance. Maneuverability is an indication of an aircraft's ability to handle the stress of a particular maneuver, and the controllability is an indication of an aircraft's ability to react to the pilot inputs. This example shows the three axes of flight which intersect at the CG: longitudinal axis, lateral axis, and vertical axis. Longitudinal runs the length of the fuselage. Lateral runs the length of the wingspan. And the vertical axis goes vertically through where those two, longitudinal and lateral axes, intersect with each other. To achieve a controlled flight, the aircraft has to be stable around these three axes. Notice that the center of pressure, which is directly behind the center of gravity, is where the lift force is moving through, and the center of gravity is what we would rotate about when we are trying to maneuver our airplane with our control surfaces to help keep it stable. And if we want to change direction, then the aircraft has to be controlled, and we have to rotate about those three axes that are moving through that center of gravity. Remember that the axis of flight is oriented along the fuselage and along the wings. An aircraft is said to roll about the longitudinal axis. Its stability about the longitudinal axis is known as roll stability. An aircraft moving about its lateral axis is said to adjust its pitch or change its pitch attitude. Its stability about the lateral axis is known as pitch stability. And an aircraft is yawing when moving about the vertical axis. Its stability about the vertical axis is, you guessed it, known as yaw stability. Rolling an aircraft is known as banking. An aircraft's heading or direction of flight is changed by rolling the aircraft using the ailerons. Let's say we want to turn left. The aircraft must therefore roll left. The right wing must raise and the left wing must descend. That means the right aileron is lowered and the left aileron is raised. When an aileron is lowered, you see in the image on the top left that the chord line, this would be the line that runs from the leading edge to the trailing edge, shifts. It goes down. And we have an increased angle of attack. That would mean that the lift increases. We have more increased lift on that wing, whereas on the other wing, when we raise the aileron, we have a decreased lift. We have a decreased angle of attack because the chord line shortened. This causes the left wing to descend in this case, and the right wing to go up. We have an increased lift on the right wing and a decreased amount of lift on the left wing. This induces the roll or banking. This changes the direction of the aircraft. And all of this happens around the longitudinal axis. As stated before, ailerons are moved in opposite directions to roll the aircraft and change the direction of flight. They're controlled by twisting the yoke to the left or right. Flaps are closest to the fuselage and are deployed downward equally on the left and right wing to slow the aircraft by creating drag while producing more lift. Flaps are controlled by the flap lever, And all of those things can be seen in the images on your screen. An aircraft climbs or ascends when lift and thrust exceed weight and drag. An aircraft descends when the opposite is true. To climb, a pilot inputs more thrust and pulls back on the yoke to raise the elevator for a pitch-up attitude. To descend, a pilot reduces power and pushes forward on the yoke to lower the elevator for a pitch-down attitude. Many people new to aviation make the mistake of thinking that causing an aircraft to yaw or rotate about the vertical axis changes its heading. This is likely because people relate flying an aircraft to driving an automobile where the heading is changed by pointing the nose of the car in the desired direction. A pilot will yaw an aircraft in order to align the aircraft's fuselage to fly efficiently into the relative wind. Relative wind is the wind that's generated by the aircraft's motion. In essence, the air flowing over the body of the aircraft should flow smoothly along it and not strike either side of the body. The rudder deflection causes the aircraft to yaw. The rudder is controlled by the pedals, and pressing the right pedal will cause the rudder and the aircraft to deflect right. When the right rudder pedal is pressed, the left automatically moves toward you. When an airplane banks or rolls on the longitudinal axis, there's slippage that occurs. This is known as side slip. In a side slip, the airplane's longitudinal axis remains parallel to the flight path. The steeper the bank, the greater the degree of slip. As bank angle is increased, additional opposite rudder is required to prevent further turning. This graphic is great. Not only does it show it in a table format, but also in an image. This shows for each of the axes the motions that happen for them, what stabilizes them, what we use to control them, and what the pilot would input to initiate that control. For the remainder of this presentation, we're going to look at different aircraft, at the different components on those aircrafts, as well as the different control surfaces. We're going to consider how a design affects the lift and drag and other characteristics. The differences are more than just aesthetic. Earlier, I talked about the wing's vertical location. You have to consider how will the wing location affect the aircraft performance. In the top image we see a high wing. The middle image we see a mid wing. And in the bottom image we see a low wing. High wings tend to generate the most lift of the three wing locations. The airflow is continuous and has minimal interruption. This also improves the pilot's downward visibility and doesn't really obstruct anything in their line of sight. The center of gravity, however, is high. In this case, this airplane has a pusher engine. You can see it mounted at the back end of the cockpit, right behind the wing, and it avoids introducing turbulence over the wing. In this example of the mid-wing, we see that it generates the least amount of lift of the three wing locations, but it does keep for more of a streamlined look, and in this case, even the pusher engine that's located at the back of the fuselage does not introduce not only vortices over the wing, nor, if you notice, does it introduce it for an empennage. This particular aircraft utilizes something referred to as a canard wing at the front of it. We'll take a look at that in a little bit. Low wings generate lift as a middle ground of the three wing locations. The airflow is almost continuous, but there is some interruption. There's an increased ground effect. This is what happens as you get close to the ground and the wind flows over the wing and hits the ground below you. You start to see that during the takeoff and landing, because of the wing airflow, that this causes you to float. Limited pilot downward visibility is also an issue with these wings, as they are literally obstructing any line of sight straight down. Then of course we have to think about the wing configuration. This is where something like a biplane or a canard wing comes into play. How will that configuration affect the aircraft performance? Don't confuse this with the vertical locations of the wings, but rather think of how the wings are configured relative to each other. This is an example of a biplane. We have an increased wing area, so therefore we generate more lift. But, as you'll learn, when lift increases, well, so does drag. Because of the increased wing area, we're going to also generate more drag. Canard wings, this would be the wing at the front end of the airplane in this case, provide major wing surface area well forward of the center of gravity. The center of gravity being farther rearward improves the pitch control. This is not a common configuration. Let's dive into vertical stabilizers and consider how they'll affect the aircraft's performance. Here we see 3 examples: twin vertical stabilizers, triple vertical stabilizers, and something known as a V-tail. Twin vertical stabilizers can improve yaw control if it's needed. More surface area also means potentially more drag. This is the example of our triple vertical stabilizers. 3 vertical stabilizers certainly will improve yaw control, and this could be needed to compensate for the limitation of other features. Not a very common configuration. And probably the least common is the V-tail. Early versions of this design made it difficult for a pilot to control yaw. Note the relative percentage of the wing that has flap versus aileron. Although we will dive deeper into propulsion systems later in the curriculum, for now let's consider these 3 different types: tractor power plant, a pusher power plant, and variable direction power plants. A tractor power plant is where you have the engine and propeller in front of the cockpit. It literally pulls the airplane along. Early airplane engines were also designed so that both the engine block and the shaft spun. That's like the one that you see here in this image. Pusher power plants are like the opposite of a tractor power plant. They literally push the aircraft through the air. A variable direction power plant isn't something we're going to see on general aviation aircraft or even most commercial aviation aircraft. We're going to see these almost always on something that is needed for a tactical maneuver, something that needs to be able to take off or land vertically. The aircraft that we see here is a Harrier jet, and it can rotate its thrust from a downward facing for vertical takeoff and landing to an aft facing direction to propel it forward. Now, in the past with landing gear, we talked about that tricycle or nose wheel configuration, and we talked about a tail wheel or tail dragger configuration. But there's also floats and an Oleo Strut that we need to talk about. Here you can see an Oleo Strut. This helps absorb the shock of landing or moving along a runway that isn't the best groomed runway. Maybe you're taking off from an area that is more of a grass runway as opposed to a paved runway. This helps lessen the shock that might happen to an aircraft's wing. You can also have things like brakes on the landing gear, and of course there's an axle and a rim that holds the tire. This Oleo Strut, in this example, will allow the airplane to also retract the landing gear into the wing. Floats are what we're going to see when we have a seaplane, something that needs to be able to land on water. They're literally pontoons, or, in the image on the top, the bottom of the airplane acts as the float. They do have wheels as well, so that they can land on the ground. In the image on the bottom, we have a tail wheel, and this wheel pivots and spins. It's not really controlled, it just allows the bottom of the airplane to not touch the ground. Notice that it, compared to the image on the top, is an actual wheel. The image on the top is where we get the term tail dragger from. We are literally dragging the tail on a skid on the back. The main gear consists of the 2 wheels that, in this case on the image on the top, retract into the wing of the aircraft. Image on the right, the bottom, will have some other main gear as well, but a good example of the tail wheel. If we look at a tricycle gear, we see that there is a nose wheel and main gear. Notice that main gear is still 2 wheels, and then a nose wheel that in this case does have a type of Oleo Strut and probably has the ability to pivot and rotate around. This isn't the only configuration, and often with larger aircraft, you're going to find that you need more and more wheels. You may even find that the type of landing gear is really important based on where you're landing, and that the performance of the aircraft isn't just how it performs in the air. Here we see a rough field landing gear. Rough field landing gear has smaller wheels to allow for larger shock absorbers. The large shock absorbers allow for rougher terrain to be something that we go over as we're taking off or landing. This also keeps the propeller well above any tall grass if you're landing in brush or if you're landing in a field that hasn't been maintained very well. And then if the airstrip that you're landing in it has kind of a soft terrain, then you need large wheels to help minimize sinking into that terrain. The size and shape and how it's configured is very important when it comes to things like the fuselage, the engine, or any kind of special configuration that might need to be taken into consideration, like this airplane we see here transporting the orbiter of the space shuttle. Aircraft can be very large. The aircraft shown here is the Lockheed C-5 Galaxy. The people shown in the image demonstrate the scale of this aircraft. Look at how they are just slightly larger than the multiple wheels of the main gear. This aircraft is used for transporting other types of vehicles. It's also used for transporting troops and other cargo that can be dropped from various altitudes. Here we see a pilot dwarfed by the size of this Boeing 777 engine. It's so large that the pilot can sit inside the cowling and head not even reach where the spinner is. The image shown here is of the final flight of the Space Shuttle Endeavour and it landing in Los Angeles in September 2012. This aircraft has been designed or even modified to perform a specialty function. It's a Boeing 747 and was modified to be able to transport the orbiter portion of this space shuttle. Although we will talk about instrument panels a little later in the curriculum, it's important for us to think about how those panels will affect the aircraft's performance. Instrument panels vary in layout but display crucial information to a pilot so that they can operate the aircraft effectively. Simple instrument panels can be used on older aircraft, but general aviation instrument panels do have what's referred to as a 6-pack, which we'll get into the guts of a bit later. I hope you enjoyed the aircraft control surfaces and components presentation. Have a great day.